All right. So last week we did an introduction, right? I hope you were quite motivated. So this week I plan to go into math because signals and systems is all about math. Now you know at least uh, signals are like your data, right? And it's a physical quantity. Like currently I'm talking and my voice is actually producing a sound wave, and it's digitized and transmitted to you. This is all through signal processing and then converted back to sound signal again. And signals are important because I think probably universe, right, is running on signals, electromagnetic waves in all the spectrum bands, right, like microwaves, we said X-rays, gamma rays, of course, the visible range of optic waves. The reason that you can see me is through another kind of waves are signals actually, right? Another kind of signal that is transmitted to you. It's actually this light. You're looking at your screen, guys, currently, right? Seeing me. Uh, Actually, you're seeing me through the light that is actually hitting your screen. And of course, my picture is already transmitted to you, but that picture is also through the light. Without light, there is no image, of course. That's the light is hitting me, the object, it's reflected right to the camera aperture, and then the image is formed on a 2D camera sensor, transmitted, of course, digitized, compressed, transmitted to you, reconstructed there, of course, and then the way you see it is again through propagation of light waves. Okay. Uh, Radar waves, we said all types of course, in communication, we use it. So, I mean, the universe depends on signals, we can say. So we will also, today, we will start with sinusoidal signals. They are very important because all these signals that I just talked about, they are actually, they can be represented as sinusoidal waves. Okay. So for instance, a music, I was asking if there are any musicians in the class. When you plug a guitar string, for instance, one of the notes, you're producing a single sinusoid. And you actually, when you start plugging different strings together, different notes, they are superposing, added together to form those beautiful melodies, right? Beautiful sounds. Those are all actually superposition or addition of different kinds of sinusoids, and almost any physical signal, actually, with some constraints, conditions, like continuity. Actually, we allow discontinuities in the signal, but finite number of discontinuities, which is fine. We can represent any signal, let's say, almost any signal, as sums of sinusoids, and that's the basics of this course. And actually, that's all you're going to learn in this course. Don't forget this sentence. You will learn in this course, any signal has frequency content, which can be written as sinusoids and multiples of sinusoids, actually. Okay? Addition of them, of course, but the frequencies will be either multiples of a fundamental frequency for periodic signals, but for non-periodic signals, any list of frequencies can be present in the signal. So you see, signals are everywhere in our lives. They are important. And one of you last time said, data is a signal. Exactly, any kind of data is a signal too. That's why it's important to know how to process signals, and that brings to, when I say process signals, that brings us to the systems. Okay, and that's like your algorithms. As a computer engineer, you guys know how to write algorithms, and in this course you will learn about systems. These are, of course, some specific systems that are dedicated towards processing again, signals that can be written as sums of sinusoids, and any signal actually can be written as sums of sinusoids, but the filters or the systems we focus on this course is, in this course, are more like filters, and filters are everywhere. For instance, low pass filters. If we typically we try to get rid of noise. Noise, we said, is a physical phenomenon. It exists in the data. Noise can be cleaned, let's say, denoised. A signal can be denoised by filtering. Typically, but this is not always, of course, noise could exist in the high frequencies. Because noise are these small fluctuations, physical fluctuations. You see, it's all about oscillations, fluctuations, actually. I also wanted to say this last time, I think I mentioned this. In physics, in a universe, all these electromagnetic waves, they are oscillating with certain frequencies. Your body has all these physical signals, biological signals, oscillating with certain frequencies. They could be periodic or quasi-periodic, almost periodic. I mean, it's nothing is perfect. Almost nothing is perfectly periodic, near periodic, let's say. So periodic means a signal repeats itself by certain time intervals. Also, another point for this course, the signals we will study in this course are one-dimensional, because you're making an introduction to signals here. One-dimensional is actually is still good. It models, for instance, sound waves and speech, and you can also think of other signals, like I was showing you last time. For instance, temperature or some financial stock price. I mean, if there is only one independent variable and one measurement, right? It's a one-dimensional data, which is one-dimensional signal. But in your life later on, if you, and probably most of you will actually focus on data science, you guys will work on multidimensional signals or multidimensional data. So a data will have many different dimensions. And last time we were saying an image is a 2D signal, for instance, or it could be, for instance, you are after, like for instance, in AI, we want to do predictive maintenance, let's say. We want to predict failures of a certain equipment. You will be measuring lots of signals there to be able to monitor the health of that device, right? So it could be the ambient temperature, like maybe moisture, because that's important. If it's a, for instance, let's just say it's a wind turbine, there is a rotor that's turning. You may want to measure the vibration of this rotor, the part that turns, right, with the blades, the vibration of it. Of course, then frequencies come into picture. And you can think of many other actually parameters, important variables. Those are your dimensions, you can say, to measure. Then, of course, the quantities are the signal values, data values. That will be a multidimensional signal. And you will write an algorithm, for instance, to be able to predict the health or status of that device, right? Of course, machine learning comes into picture, but signal processing, data processing is always the first step in preparing the data for further, more advanced algorithm development. Okay. Also, mathematics here in this course, also in other like machine learning, deep learning, computer vision, natural language processing, robotics. I mean, mathematics is very important because I was telling you again last time, you should really be fluent in math. Mathematics is the language of science. Guys, you guys can call yourselves hopefully in a few years, computer scientists / engineers, let's say. So you will become scientists. So you should be fluent in the language of science, which is mathematics, okay? So this course is a lot of mathematics, but there is also a lot of course, physical relevance applications. So you will be implementing also the math that you're learning here, like filters, compression, spectrum representation. You will be representing all kinds of things in Python, which is, I think, a good practice. Okay, so with that introduction, let's get started. Let me share my screen. I think I can go to my tablet, but it's not. Oh, okay, it's there. So guys, let's get started. Uh, so let's get started with math. I will try to, whenever I find, I will try to show you some motivating video. Okay. So we said actually, let me have my notes here also, just to follow. So let's say, guys, you can see my screen, right? Everybody? Okay.
Yes, we can.
Yeah. Yes, thank you. Yeah, you can just open the mic to say and answer a question. Okay, guys. So let's get started. It's all about math. It's important that you go over this math after the class during the week. Okay. A signal. So what is a signal? What is a signal? Okay, it's a quantity. Okay, a quantity that varies over time or space or any other dimension. Okay, over time or space, or it could be, of course, this is 1D, 2D, but it could be 3D or more. For instance, video signal is 3D, or it could be medical signals. Okay, medical signals are 3D. Then you have 3D medical signals, like a cardiac, for instance, medical signal. Just imagine you want to measure, just to know the status of your heart. You go to a cardiologist, they may order, and for instance, cardiac MR, which because your heart, your body is in 3D, of course, MR, magnetic resonance imaging, gets signals from your body in 3D, but also your heart is pumping blood, so it's expanding and compressing itself. So that would be a 3D volume in time, right? That's a four-dimensional signal. Maybe we have 3D, 4D, etc. I mean, it could also be, like I said, all kinds of data you're measuring, like I mentioned. For instance, for predictive maintenance, you get device measurements. Those are n-dimensional, however many collections, measurements you can make. Okay, and the, of course. So, but mathematically, it's a function of an independent variable. So it's actually, we could say, a signal is a function of an independent variable. It's not, of course, single. Maybe I should say, sorry, not n, but is a function of independent variables, let's say. Okay. So this is, I know, currently high school math. Let's say variables, because for this course, we are typically talking about signals like this, guys. See, because it's easy to start signal processing with one-dimensional signals. For instance, if you were in EE, electrical and electronic engineering, you could take an advanced signal processing course, maybe a follow-up where you see multidimensional signal processing, or it could be a graduate course at the EE program. And I was telling you, this field was, of course, first introduced, developed by electrical engineers, but it's very important for computer engineers too, because you should really know how to process data. You should know data also has frequency content, how to filter data, right? For instance, convolution operation, you learn it here. And no, you guys know CNNs, probably you've heard convolutional neural networks. The basic operation is the convolution there, okay? But you will be learning the frequency perspective also. So actually, so when I, for instance, I say, hey, there is a signal, it could be infinite extent. This is, let's say, t, of course, here I should say t, f of t. So you guys know this is a 1D function of time, okay? 1D function of time. telling you an image, for instance, IXY, a 2D function of space. This is an image, right? For instance, this is an image function. Okay, so guys, I could have also, of course, discrete time signals, by the way. Maybe this could be a time to also talk about those. I could say, now I discretize, you took numerical methods. Now T is discretized. Okay, it's like this actually. I sample. Let's try to do it on here actually. Yeah, it would be more, I think, telling. So it will be sampling. We will see this. We will learn sampling in the frequency domain. So in this course, you guys will learn to work in two domains, both the data original domain, like the time domain, space domain, and then the frequency domain. This is like a transform domain. We are transforming the signal or data into another domain for better processing. For instance, for certain tasks, frequency domain processing will be easier. For instance, extracting certain frequencies from the signals, okay? Because I know in the frequency domain or Fourier domain, here in our course, Fourier is a big name, probably the most important name for signal processing course. And most important scientists historic from the history, because Fourier was Joseph Fourier, a French mathematician, guys. He was the one who actually found out that any signal can be represented as sums of sinusoidal signals. And then we add those sinusoids, and the coefficients are called coefficients. Okay? That's a transformation. I can compress it to another domain. Oh, can you hear me, by the way?
Yes, we can right now, but
okay.
it is a little bit laggy.
Yeah, let me see.
Like sometimes.
Sometimes, is it happening sometimes?
Yes.
I mean, from the start of the, from time to time, okay.
It started when you started sharing.
So guys, so we said here is, or let me call this x of t, by the way. X of t, 1D function of time. Now I will sample, okay, let's go also, every, for instance, ts seconds, or every t seconds. So let's say I start here, 0 ts, 2 ts, 3 ts. So I'm you see getting x of 0, x of ts. So actually I will have a, so let me just maybe do it similarly somehow, try to replicate the signal. So it will be really this time here, guys, the discrete time signal will be, we denote it like this. So this discrete time signal, by the way, this was a continuous time signal. This is important to know. Okay. Now x of n, this was x of t. T is a, you see, t, a continuous variable, right? Now x of n, a discrete time signal. Okay. Now my n is just an index, right? An integer index. From here to here, we go by sampling actually, and from actual discrete time to continuous, we can go by interpolation. We will talk about those later. But now I sample x of 0 and write it here, guys. So let's see, this is x of 0, you see 0 index. So let's see, this is x of 1, this is x of 0, x of 1. But actually, normally, this is x of ts, right? So it's actually exactly like this. I think you got the idea. 2, 3, 4, 5. Okay, you can sample your signal wherever it exists. Then this would be these discrete Let me see, somebody made a comment. Yes, I will be sharing them. But if you want, some people, Metin understands better while, you know, taking a little bit notes. I recommend everybody takes a pen and paper next to your laptop or desktop because it would be, I think, better to maybe write some things down. Today you will have a quiz. Our quizzes start. Also, you will need a pen and paper, pencil and paper, okay? But I will be putting these online to the Ninova, right? So, guys, this is then, we said this is a discrete time signal, okay? N is an integer index, T is a continuous variable. I hope you get the difference between, and we can go between the two, okay? So this way is continuous to discrete conversion. You may have heard of this from analog to digital, and this is discrete to continuous or digital to analog conversion. Okay, we will talk about those later. So maybe now I can talk about sine waves now. Okay, so maybe let me still write this here. Continuous to discrete or analog to digital, just for your notes. Analog to digital conversion is x of n, and there will be a way to interpolate this and make a discrete to continuous. This is digital to analog. So can you think of systems? And these are systems. These are converter systems. These are, you see, also systems. So systems are some, we said, actually mechanisms to manipulate systems, right? To signals. System, this is a system, D to C converter, discrete to continuous converter. This is another system. Okay, so can you give and think of an example, guys, that converts an example system that converts a continuous time signal to a discrete time signal? We are using it now. I am, and you are when you're talking. Microphone, thank you, Ekta. Exactly. Yes. Yes, MP3 files, thank you, Tukan. Yeah, exactly. The MP3 files are those discrete signals that are also compressed and stored. Then the excellent microphone has this actually transducer which converts a physical continuous time signal to a discrete time signal, meaning actually these x of n are really, guys, you can see, for instance, this was 0. I'm just making up these numbers, 2.3, maybe 4.2, 5.6, etc. It's just an array of numbers, right? So this is really your arrays, vectors, if it's multidimensional matrices and tensors, right? In our multidimensional case, it's tensors. So these are really vectors, matrices in 2D, 1D, tensors, and the. Okay? So, and now give me an example for discrete time for this one, discrete to continuous converter system. Just think of the reverse of, exactly. Thank you, Fuat. Yeah, the speakers, your speakers currently, or even your headsets, in your, of course, laptop, you have to have speakers. That's the, exactly. See, green is another example. You're right. It converts, very good point. These images, digital images, right, to actually these, we could say, physical patterns that we can see. Thank you. Very good. Great. Great class. All right. So now let's go to sinusoidal signals. Okay. So for this course, we said sinusoidals are important. Okay. So let me see. I could just go maybe sinusoidal signals. No, just a sec. So we will talk about these guys. guys. X of t, let's say, let me give an example. A sine, this is a generic form, omega t plus phi, we will be talking about, but maybe before that, can you, or maybe no, let's just a note. I think you guys recall this easy one from high school. Probably you guys all have worked with this one, because this will be a little bit newer now, because there is this argument, angle argument, which varies with time. That's the difference. So you guys are probably used to this, right? Sine theta. Theta is in minus infinity to infinity. Of course, this is a periodic signal, but let me just introduce this first, and then this repeats itself infinitely. It oscillates, right? Let's say x of theta. Of course, this is my theta axis. So let's just write pi over 2, 0, pi, 3 pi over 2. I mean, this is something you guys know. So minus pi over 2. So, and the amplitudes here, you see the A is the amplitude. So for this signal sinusoid, you are used to, these are 1, or of course it could be 2, or let's make it 2. So maybe 2 minus 2. Now, remember also this one, sine theta and cosine theta, remember, are just related by what we call a phase shift, right? This angle of pi over 2 difference actually. And theta is in radians. We should say theta, it's a dimensionless quantity, but we call it radians. It's the angle argument, okay? So arguments of sine and cosine, I mean, they are the same signal, right? Cosine is radian. So when I draw two signals, or say two signals are related by a shift, I will assume you guys know how to plot the other one. That's a shift, right? In I mean, pi over 2 shift, right? So it's, I mean, of course, the peak will be here. Sorry for this. Please check your textbook, guys. It has nice pictures of these sinusoids. Okay. So now, then that would be, for instance, 1 cosine theta. Now, this is pi over 2, 0. You guys know these, I think, already. So pi and 2 pi, etc. Okay. So that's my cosine theta. Now, we make, you see here, notice sine, this theta, now we make it omega t. Let's just maybe forget about the phase for a moment. Now, this is important because W is my frequency, okay, here, because T is in seconds. So what is the then unit of W? Because we know this should be radians. W is radians per second, right? We say rad per second, radians per second, let's say. Okay, I said SCC, but okay, let's write it fully for the first time. Radians per second. Okay, so then, so that my WT is in radians, okay? That's called, this W is called my angular frequency. It's an important parameter in this course for you, okay? And we will also relate this is frequency, okay? Angular frequency, we relate it to the regular frequency you guys are probably used to, this 1 over seconds, 2 pi f, okay? And f will be the frequency of something, it's 1 over second, meaning, I mean, its unit is 1 over second, okay? It will be actually 1 over period, t. So how much something repeats itself in a second is frequency. And this is also hertz. You guys are used to hertz, I think. We are talking about, for instance, radio waves all the time, tuning to radio stations. Those are all remember actually stated in terms of the frequency spectrum of that or frequency band of that radio station. Okay, so now let me plot maybe then this guy again. Let's say this time let me just plot a cosine omega t plus phi, and we said phi is a phase that should be in radians, okay, also. And this is my amplitude, I already said, and this omega is 2 pi f. So now let's plot this guy and let's continue from there. Now I have, try to plot this nicely. You will see the importance of this signal. You may be like, hey, why am I spending too much time on this simple signal? This is the basis function. This is one of the basis function for our Fourier series, Fourier transforms, guys. We will be learning about signal processing in this course, right? Signal processing. So maybe let me write this, manipulating. So signal processing, manipulating signals through systems, and these are like your algorithms, right? Okay, your algorithms. You guys are taking algorithms currently. So there is an input x of t, let's say, input, and then a system. We've seen already example systems, right? So and an output system s, let's say, and an output signal. And for instance, Fourier series, Fourier transform are really helping us to design systems like filters, for instance, frequency filtering. And this ties to also, and the signal representation will tie to Fourier series and Fourier transform. Okay? Fourier transform. We will talk about those, don't worry. So let's maybe, okay, go back to our sinusoid representation. Let me plot this guy. So we have, I will plot it with a little bit phase. Okay, so let me try to plot this nicely. I mean, you guys imagine, of course, this is really repeating itself. It's really not different signs. I mean, it's you guys should please check the book for I mean, it's of course the same amplitude A here and the same amplitude minus A here, okay? Minus A here, A there. This is my x of t signal, okay? And then I have here, I'm going to tie this f. F is very important. We said f is the frequency of this signal. So this is a single sinusoid, a single tone signal. F is here important. Now, how do I can ask you, how do I calculate F, for instance, from this time plot, time domain plot? This is time domain representation of my signal. Main representation of my signal. You will learn about frequency domain. Period, right? I think some of you are already answering exactly T. Thank you guys, 1 over periods. 2 pi over T is for the W, the angular frequency. Perfect. Thank you. So guys, for instance, you find 2 peaks and this period, the time interval is your T in seconds, okay? And from here, F is 1 over T. And exactly like you guys said, the angular frequency will be 2 pi over T, or it's also equal to 2 pi over F. So this is Hertz, and this is radians, okay? T is in seconds. So, so you see a period is where one cycle of a periodic signal happens, right? That's the duration of one cycle. So please note all of these. And why is this important? Maybe I can, actually, I had some, I will share my screen and we can listen to, I remember opening some single half tones. So guys, here are some sinusoids, because when F changes, so let me, okay, you can see my tablet currently. So when that F changes, my frequency, the period changes and frequency changes, right? So when frequency is low, what kind of a sinusoidal you expect? And when frequency is high, what kind of a sinusoidal you expect? Please think of it. And also think of the sound waves, the low frequency, high frequency, right? That's the idea. Low frequency signals are those bass signals. So let's try to hear this. Let me see if okay, it's open. Can you hear this? Let me play, guys. It will start playing from 20 hertz to 20 kilohertz because we, human auditory system, we are limited by that range. And even some of us are losing the ability, either as we age or at least maybe, I mean, from birth, we may not be really hearing those very low and very high frequencies, okay? So let's try to make this test. This is also hearing test. You can check yourself. Can you hear?
No.
Yeah, because it's very low still. Let me increase the speed a little bit.
Hocam, I think you're not sharing sound.
Really?
Either that or I'm not hearing you.
No. You guys are not hearing. Did you hear? These were too low. I'm gonna scroll it a little bit. Let's see. Because that's a great, you see, guys, experiment. We really, we say it's 20 hertz to 20 kilohertz, but it's gonna start later. Just wait. Some of you also, you guys can talk. Yes, it's not the speed I'm actually. I see. Let's maybe keep I see. Yeah, let's not change the playback speed. So let's go. I can scroll a little bit because I think we are having problems. No. Guys, so probably it started somewhere around 30s. I will scroll. You see the humming sound? Right? So each of these sine waves are a single tone oscillating at a certain frequency. For instance, the one we see here is 34 hertz. Of course, here they are increasing it every second or so. So please also, guys, pay attention to the form of the wave, the signal or waveform. The signal will start oscillating with much more rapidly, right? Maybe I can make this way. Let's go a little bit more. You see the signal? 268 hertz. Let's go a little bit more. You see, high frequencies are a little bit disturbing. You guys are still nothing. Ekrem, you should check go to an audiologist and check your ears. I'm sorry to say it, but you see around 30, 40 hertz. Everybody, okay, probably it's your headphones. I mean, you guys are young, and it's okay to just miss some of the frequencies at the low and very low, very high ends. But actually, as I know, as we age, guys, probably I hear a little bit less. Mine starts a little bit later than yours. These things we lose it a little bit. Like, yeah, you're right. But Mustafa, that's a great comment. High frequency sounds like air raid siren. Actually, we will take now, our goal in this course is, guys, to be able to decompose any signal into these frequency components. So that's why sinusoids are very important for all kinds of math. For data scientists, for signal processing people, for you, computer engineers, EE engineers, because you can decompose any signal into sums of these sinusoids. And then you see we can really just grab whatever we want, right? It's really like feature extraction, okay? And siren, your question is good, your comment. Sirens are more like what we call beat frequencies, or if you actually you can maybe you're also right actually, if it could be two ways. Beat frequencies are when we multiply, remember, two sinusoids together, or when we add two sinusoids we can rewrite them as equivalently, either as multiplication or as sums. Either it's multiplication of a small and a large frequency sinusoid, or addition of close frequency sinusoids. It's equivalent. That I will show you some maybe siren sounds later when we do that beat notes. But also remember last time I showed you a chirp signal, which is like a bird's chirp, birds singing. That was actually very high switch, like here, from like a continuous actually increase in the frequency, switching from one frequency to the next, but to a higher frequency. Good. So let's just maybe, it's becoming a little bit disturbing for me. I'm also now more sensitive to these things than you guys. Let's go a little bit more. And at the other end, guys, high frequency, you guys will probably continue hearing more. Some of you will hearing more of the high frequencies. We call them high pitch frequencies. The lows are called bass, remember? So let's continue a little bit more. Okay, I try to increase these. For me, it's a little bit too much. You see the frequency, the rapid oscillations now. And let's go a little bit more and let's see, maybe I can still hear it, of course. Guys, it's very, very high, 5 kilohertz. Let's go to 10, almost 10 kilohertz. I think this now, I hope it materializes now in your mind, the sinusoid signal. As you change the frequencies, you see you are really probing all kinds of possible signals, one-dimensional signal components out there, which is great. Because now combining all these guys, I can create any signal. That's amazing, right? That's an amazing result for mathematics. Okay? Okay. Fixed hertz sounds. I don't know what you mean, Resul Levent, but focus fixed hertz sounds. Okay, you can, if you guys want to show demos and things, please send to your assistants, Yusuf and Frat. We can also just play for a few minutes those things, okay? So guys, let's just finish this. We can just try to see when we break. Okay? Let's see. I can still hear now. For me, it's gone. Can anybody still hear this? No? Maybe. In class, we did this last years, of course, guys. Yes, I agree. We are doing online. Last year, we did our first 4 or 5 weeks in Signals course physically in campus. Remember, it was March 15, but we started, I think, around 7th of February that time. 5-6 weeks was in class, and we did this experiment in class. I remember some students continued to hear really to these actually end of the spectrum, but currently probably, yeah, it may be due to Zoom. All right, so you see it's gonna go till 20 kilohertz, but that's it. Okay, so I hope this is clear, at least the idea is clear. Let me escape this. Let's stop share, go back to our notes now. By the way, it's 50 minutes. We are actually instructed by Jörg and the focus school not do more than 50. Even they said 40 to 50 because these are online classes, and of course it's very normal. You may not focus after 40, 50 minutes. Okay, so let's give 10-minute break and come back, okay? Because we started at 8:30. All right, let's continue. Guys, let's see. I will, by the way, assume you guys know how to work with sines, cosines, but let's maybe do actually a few things here. Let me connect my... All right. You can see my screen, right? All right.
Yes.
Yes, thank you. All right, so can I probably, maybe let me show you will be, because sinusoids are important, you should be able to work with sinusoids. Like for instance, now let me give you this guy, cosine, let's say 3 pi t plus pi over 3. Example, let's say. So now I will ask you, what is the frequency of this sinusoid? Plot this guy. What is frequency? What is phase? Plot it, for instance. You should be able to do these things. And also, for instance, find the peak position, first peak. Find first peak of the cosine. Let's do it together, okay? So don't worry, it's a time signal. So I assume there is a phase shift, guys, right? It won't be exactly, the peak won't be at 0, right? So it will be something like this. I mean, it's of course a little bit rough, but it's fine. This is, let's say, my peak. I'm after, this is T0. First peak, it could be in either side, but let's see which one I will be finding. I will understand it once I do the math. So first of all, what is the angular frequency? I want to ask you. Now you guys know the main form of the signal. So just go back, look at this signal here. The angular frequency is this guy, right? W. So what is the angular frequency? Angular frequency is W is 3 pi, right? Are we fine? And what is the unit? Radians per second, okay? Then from here, what is the standard frequency? Let's say the Hertz frequency, F, right? You should just divide it by 2 pi. So 3 pi over 2 pi, which is 1.5 Hertz, right? This is it. What else can we find? From here, I can find, from the frequency, I can find the period t, which is really 2 over 3 seconds. Okay? So now I can also find this peak t0 location. I can set for t0, set the argument of the cosine to 0, right? Because I know it's a peak. Cosine 0 is a peak. If it was a sine, you have to just be careful. What you find would be, for a sine, if we set the argument to 0, that would be the first zero crossing, okay? To 0. So I would have, from here, t is minus pi over 3 over t0, 3 pi. Okay, so this will be minus 1 over 9. This is really exactly my, let's say, seconds. Minus 1 over 9 is the first peak. And then here it's 1. The peaks are at plus minus 1. And let's also maybe label a period here on the plot between two peaks. I know the length of this, right? This is t we found as 2 over 3 seconds. Okay, so you see, from a plot, I can go to the signal mathematical expression, and from the signals expression, I can go back to the plot. Okay, this is what you guys should be able to do. So now this is clear, right? I mean, these parameters are important, and phase, of course, we should write phase. Phase is phi, which is pi over 3 radians. Okay, so all parameters. And A amplitude, let's also put it down. Amplitude A is 1. So these are really A, W, also F, I mean, they are related, phi, right? T0 is dependent on the others, which is fine. These are parameters. This is also, of course, they are interchangeable parameters of the sine wave. I use, by the way, sine, cosine interchangeably because they are the same thing, but there is just phase shift, okay? Very good point. Change of phase, thanks Hasan, is actually shift, time shift, right? Leads to a time shift here. You see, this was, T0 was minus phi, right? Over W. So, I mean, of course, normalized by the angular frequency, phase shift corresponds, phase shifts in this angular domain, angular phase shifts or frequency domain, you can say, corresponds to a time shift in the time domain. Thanks for this good question. To a time shift, okay, in the signal. So maybe I can, I will assume this is all clear. I hope it's clear. I want to make a definition, two things. First, shifting and scaling signals, and then I want to define periodic signals. Let's maybe define periodic signals first. Periodic signal definition. Definition is, guys, if I can say x of t is equal to x of t plus t, right, mathematically, but this is for all t, then this is if then x of t is a periodic signal. Is a periodic signal, and t, and let's say t is a period of x of t. Okay, this is important. For instance, example, I can ask you x of t is 3 sine 4 pi t plus pi over 8. For instance, what is the period of this signal? I mean, it's periodic already, actually. This is not an example to this periodic signal. Anyways, find the period. This is find the period of this signal. Already we know sinusoids are periodic signals. Periodic signals. I mean, this was a no-brainer, right? You can find the period, but there could be other types of signals that repeat themselves. For instance, I could have a triangular wave. We call it a triangular wave that repeats itself. Okay, it could be a rectangular pulse. Maybe in your digital circuits, you've seen such signals. No, but probably this is more analog circuits type. I mean, it could be, of course, different periods, right? Let's maybe make this a little bit different periods. And it's going like this. And in this direction also repeats itself. So for instance, here defining the, and other examples, these are other examples, defining the period, find the distance between two peaks, right? This would be the t in seconds. Similar to here. For instance, here to here. I mean, it could be any two peaks or any two repeating pattern locations, right? T in seconds. So these are all periodic signals. Examples, periodic signal. Of course, it could have some more crazy pattern in between here. It could be a much more different periodic signal you can think of. These are some examples of periodic signals. So let's now just talk about this very quickly, because I know you guys already know this, shifting and time scaling signals, but every year there is a confusion in this, in the students. So in the first class, we do this. I just note this for your notes. Time shifting and time scaling of signals. I mean, I think shifting is easy, everybody knows. Just consider, e.g., consider a signal like this. Let's say it's -1 to 2 t x of t. Now let's say I shift this by 1 and I want to plot this signal. I know it has now displaced itself, right? It's translated really to now here. Exactly like this, right? 0, 1, 3. This is clear, I guess. This was, let's say, 1. This is easy. Now time scaling, and you should also remember these rules. These are important because, for instance, when we study convolution, there will be a filter and a signal, filter signal, and the signal itself. The filter will be, for instance, swapped now, time scaled by minus, and then shifted over the signal. It's like a correlation operation in a different way. So you should really know what these things do. So this is really moves x of t to the right, if t0 is positive, of course, this to the right by t0 seconds, right? And if it's the other way around, t plus t0 moves x of t to the left by t0 seconds. It's the same thing. This is important here, okay? Now time, this was shifting. Now time scaling, remember, maybe a little bit trickier, you could say, okay? So this was my signal. Let's keep the same signal, okay? -1, 2, x of t. Now let's just maybe actually do x of 2t. Remember, this is time scaling is this, right? A could be bigger than or smaller than 1. For instance, let's look at x of 2t. This was x of t. Now this guy, on the contrary to maybe just seeing it like 2t, it's gonna compress, right? So it's gonna be really -1/2 to 1. The signal is now in this way, t. But if I had vice versa, like x of t over 2, now the time a is here, you see a is greater than 1, a is less than 1. Now I have to really expand the signal. -2 to here, 4. Okay, that's it, 4. T, and also if I now have a negative t, my signal will be really mirror reflected, right, for this one. So this is really -2, 1. This is the x of minus t, okay? So I think these are clear, but now combining these, we should note this both shifts and time scale. There is a rule of time, both time shifting and scale, shift and scale. Rule of thumb, guys, first shift and scale. Easier. I mean, you could try to go the other way, but rule of thumb, first shift, then scale. Okay, so let's see an example. This is, I know, a little bit like first year calculus. So I mean, for both time shift and scale is really like this. Y of t is x of at plus t0, let's say. Yeah. So for instance, example, y of t is x of 2t. Let's make this nicer. 2t minus 2. First shift. Let me take the same signal. First shift. It was 1 and 2 here, x of t was here, our sample signal, right? I mean, of course, rules don't change. Now shift, let's call this signal z of t. I will shift this guy by 2. Okay, let's shift by 2. So let me then maybe make this larger or longer. 1, 2, 3, right? Good. Or sorry, 4. It's a 3 length signal. 4. All right. So this is 2 because it goes, I mean, the magnitudes don't change in this one. And now time scale is really compressed this guy, but it's gonna then move 2 becomes 1, 1 becomes 1 over 2. Okay. So now this is the y of t. It's really be 1 over 2 to 2. 1 over 2, this should be 1 and goes to 2. Okay, this would be really the resulting signal. Okay, so I think students were getting confused last year when I defined, for instance, z of t is equal to, first of all, this is easy, x of t minus 2, first shift. But then we define a y of t, which is equal to z of 2t, right? Because I just scaled this by 2t. Now, but my y of t really becomes x of 2t minus 2, okay? You see, scaling just here acted on the time scale axis. So be careful, you can check this yourself. I will give an exercise for this. Please do the exercise on your own. Do the exercise. So guys, this is the example I'm giving you as an exercise. And you see, signals and systems course is not difficult at all, but you just have to sit down and maybe every week do 1 hour practice, read the notes, to solve the exercises. Of course, when the homework starts, you will have to do more, but I think they will be starting this week or next week. But you will have fun with the homeworks. Don't worry. So let me give you an let me see. My exercise to you is obtain this start with x of t is cosine, maybe I should give you just t, cosine t, and then obtain y of t. Okay? Yeah, I think that would be a good exercise for you to apply these rules. Okay? If you want, I could plot it, but maybe we could move on. You can do this, right? Guys, do you want me to solve this or can you do it on your own? You can, right? Let's see. Okay, for this first one, yes, Ali. Okay, let's solve it together. It's very new. You guys are just warming up to the semester. So start with a cosine t. So let's first plot a post cosine t together, guys. So maybe how many plots? I will have 3 plots. So let's just keep the space open for it. So cosine t, we know, has a form like this, and I know it should be pi over 2 here. Pi, it's minus 1, of course. I mean, it says to be minus 1 here, guys, of course. So just okay. So pi 3 pi over 2, 2 pi, etc. You guys know the, story. So this is really cosine t. Now I will add a pi over 2 shift. So first shift, start with this. First shift by pi over 2, okay? So I know it's gonna be a sign actually, so I already can, sure, I have to be careful in drawing this. My peaks should be here and my zeros should be here, right? Pi over, okay. I mean, you guys get the point, but anyways, not nice. Guys, I mean, you get the point. So anyways, 0, pi over 2, pi, etc. 2 pi. This is now shifted signal. This would be cosine t plus pi over 2, right? Now, scale, guys. Sorry, Muvar. I'm sorry. People are asking questions now. No, you guys are right. But here it would be the same, right? It's symmetric. We should, like you guys said, it's plus pi over 2. I shifted left, but it's, you guys are right. I know it's not the same. Thank you. Thank you. I thought to myself, that's why I didn't really, I thought it would be the same thing. It's not. Thank you. I have to, it's a plus pi over 2. I was shifting minus pi over 2. Thank you. I didn't really pay attention. Guys, I have to, like your friend says, thank you, but it's good actually we worked it together. You have to be careful. Thank you. I really have to shift it left, so the positive peak comes to the left side. Thank you. So let me not be that careful in terms of the peaks and other places, but at least here, let's just. Oh, I can't. It's difficult now. It has to. Okay, it has to be really like this, right? You guys, I think now got the point. Now I have this, and yes, thank you. Shifts to the left. Shifts to the left because pi plus pi over 2, okay? Shifts to the left. Okay, perfect. This is, let's write it on top of the, here, plot t plus pi over 2 for your notes. Shifts to the left, we said. Perfect. Let me write some of these places here, pi, 2 pi, etc. And this peak is at 3 pi over 2. Perfect. Now, let's now do scale by 2 pi. So that would mean, guys, my time axis here, I will actually, because it's times 2 pi, I will divide all those by 2 pi. Time axis scale. Okay? That's the idea. I think, yeah, it's good we did this together. I believe you don't see this in high school or somehow in calculus, you overlook this time scaling signals. So you may not have paid attention. So this was my minus pi over 2. Okay, this was minus pi over 2. Now, minus pi over 2, I have to be careful, will become, because I'm dividing by 2 pi, 1 over 4. I have to, let me see, the same thing will be really squeezed by 2 pi. So I have to really squeeze it. Just let me try to squeeze this. First, I will plot a squeezed signal sign. Okay, it will be, you see, I mean, you see its frequency is changing, right? Scaling 2 pi, actually we're increasing its frequency. So, I mean, amplitudes don't change, of course, all are 1 here, minus 1. Let me write some of these points here because this guy now, it was pi over 2, right here, it was now divided by 2 pi, this now becomes 1 over 4. These are seconds, you should always put the units of your plots, 1 over 4. Then I have, for instance, this guy was pi, right? No, this was pi, divide by 2 pi, 1 over 2. This one was 2 pi, it becomes 1. And the peak 3 pi over 2 over 2 pi, this becomes 3 over 4, right? Correct, right? Okay, it's good we did together. So what is this guy then? It was minus pi over 2, this peak I'm after now. It has to be time scaled by 2 pi, so this is minus 1 over 4. All right, so 1 minus 1 are there. So this is really now, sorry, it is really, the signal is, okay, y of t, this signal is cosine 2 pi t plus pi over 2, okay? And you see, it looks simple, but still, we had to be careful. Great, I think it's okay, perfect. Guys, I think, okay, so also do the exercise, do another exercise on your own, okay? So maybe, let me see what else we have to cover here. I will give you another exercise for plotting a sine, cosine exercise. Let me give you this. Plot this, okay? Plot x of t, and I will give you an shift and scale exercise. So 7 cosine 0.2 pi t plus 0.8 pi. Okay. By the way, you guys can say this is the phase, right? But this cosine and sine, they are periodic with 2 pi. So if I had plus minus 2 pi, it would be the same, right? So phase is really ambiguous, meaning we can add multiples of 2 pi or subtract multiples of 2 pi. We still get the same signal. So, sorry, that's ambiguous. Okay, just be careful with that. It's the same signal with this one also, same signal. So now I want you to find as exercise W, F, phi, T, the T. Please find these A, of course, all parameters, okay? Find these as parameters. You guys should find these and plot it, all right? All scaling like this, it's time, but if it's, for instance, space image, you have to then do, you will have 2 dimensions, right? 2 independent variables. You do these to each axis separately. Okay, good question. For multidimensional signals, no, it still holds, but it has to apply to each dimension. Good question. So guys, find also the place where it has a peak. First peak, time points. Find all these, okay? So my point is, please do this exercise, plot it also. So my point is, given a sine or cosine pilot plot, you should be able to go from, either you should be able to write down these parameters of the signal, okay? These above, these guys of the signal, these parameters, I mean this, okay? Then, of course, that takes you to the mathematical expression, okay? Mathematical expression. And also, you should go from mathematical expression to the plot. Okay, I think that's fine. Now, we will do one more thing. I can assume you guys are really either cosine, sine, you are on top of, or you understand what this means. This is a real signal, by the way. Now we will make a mathematical abstraction because that mathematical abstraction of taking this real signal or real sinusoid to a complex sinusoid, it's gonna really actually help us manipulate signals much easily. So now from here, this was real. We will go to the complex sinusoids and complex plane. We go to a complex sinusoids because they are the basis, guys. They are the basis of our Fourier transform. Also Fourier series. We can also, of course, express them with real basis functions, but like I said, complex representation is much easier to manipulate. That's why. These are mathematical abstractions you should really feel comfortable with, and you should not be like, why do I need to do this? Okay, that would be a very lazy and inappropriate thing to say. So now we take sinusoids to this form, a e to the j omega t plus phi also, of course. I know it looks strange. That's why this is a complex sinusoid, okay? So don't get confused. Really, it's nothing. You will see that this has a real and an imaginary component, which are both sinusoids. It has two sinusoids in it. That's it, actually. We will see now. So to do that, let's say this. Complex numbers for us, or complex plane, will represent sinusoids for us. By the way, what are these basis functions? You may be wondering. Either in discrete or continuous time, but maybe okay, let's write maybe discrete time is easier. I was telling you maybe last time, or maybe I didn't have time. There are some maybe, let's say, and I should write here a coefficient, some basis functions and some coefficients. I mean, this is really just a very rough argument here. So here, what I'm doing is writing my signal. Typically, these are minus infinity to infinity, but of course, some of the coefficients may not be really important. They may be 0 or very close to 0. And these psi are the basis functions. So this means in mathematics, actually, this is done a lot, not just signal processing. Signal processing is a math course, actually, but as computer engineers, we implement everything in the computer digitally. That's why we have to realize these mathematical models in the computer through implementations, right? Coding. Let me see, I think there is a question. Yes, Oz, your question for the first peak of cosine, we set argument to 0. For the first peak of sine, yes, set it to pi over 2. Also, you can set it to 0 for the sine to find the first zero crossing point. Good. Okay, so these basis functions, in this class, mainly they are sines and cosines, Fourier bases. We will be signal in this course, they are Fourier basis functions, and they are actually complex sinusoids, but which have its real sinusoid components. What other basis functions in theory we have? Like wavelets, for instance, are basis functions. Just search yourself what other signal decomposition or basis functions I can project my signal onto. This is really like projecting a signal onto this basis function. Then I can store only the coefficients. And because I already know the basis functions, you can view them as building blocks. You add them, take these CKs, a number of them, add them up with certain weights, weighted addition, you actually construct a signal, okay? This is really decomposing a signal onto, or projecting a signal onto a space. Here it will be Fourier space, and that's why I'm telling you about these complex sinusoids now, because these guys are my basis functions, okay? They are very important. So please pay attention. So now complex number system, just recall, make a recall. This is probably you've studied in your first year calculus. You will remember. This is really complex number space, complex plane. This is really extension of a real numbers plane. Extension of real numbers. Remember, I had a complex number. Now you see signals and systems. That's why some students somehow fear this course. It is really very easy, but you just have to pay attention and just think that these are really doable, very straightforward things. So think of a complex number, x plus jy, right? This is a Cartesian representation, remember. I have a complex plane. Remember my z plane, complex plane, This is the horizontal axis was the real, the other one was the imaginary, remember, the vertical one, the imaginary axis. You see this is an imaginary number, remember RJ, imaginary. This is my real, this is the imaginary part of this number. So it's really, let's say, X and Y, and it's really like a vector actually. Z is here. Remember, on the real space, real dimension go by X. In the imaginary dimension go by J, but here it's really X plus J, Y, right? That's it. So if, for instance, I have now Z equals X minus JY, I would have to really go down, right? Maybe let's use another color now. Where am I here? Now this would be actually, let's write it in this color. Z is X minus JY. Please pay attention. Okay? Remember this is the conjugate actually. So this is really Z star, conjugate of the complex number. Just to remember these maybe identities, Z square, it's not the Z square, I should have said J squared here. Sorry, J squared. J is that imaginary number, remember. It's actually sometimes also defined as the square root of -1, remember. Then you can find all other multiples minus J, right? J to the fourth is then really 1, and you can continue in this way. You should remember these. Okay, J to the 5 is J, etc. Okay. Now this is clear, right? You guys remember this was the Cartesian form. X plus jy is the Cartesian form of the complex numbers. I have also a polar form. I will complex number. Now let's write it in polar form. Remember, this is also very important, guys. Z is r e to the j theta. You remember this? What is r? The polar coordinates. Maybe you've seen it as Cartesian coordinates and polar coordinates. R is, of course, the magnitude of that vector. So maybe let's go to the next one here to really plot this in a nice way here. So I said I have a Z here, which is, let's say, let's make the R equals 1 e to the j theta, okay? This is also X plus J, Y, right? Real plane and imaginary, real dimension and imaginary dimension of my complex plane or axis. So remember here, important thing was this is R, which is the magnitude. Here in this case, it's 1, and angle is the theta, right? So R is really X squared plus Y squared, then square root. Theta is the arctangent Y over X, right? This is X, this is Y. And actually now, if it's 1, when it's 1, I know this is really cosine theta. I mean, it could be r cosine theta, but just for this case. And this Y is sine theta, right? I mean, because the radius, the hypotenuse, this guy is 1, right? From this triangle, you guys can see this, right? This and this. Cosine theta, sine theta. So actually you can see that my Z, which was e to the j theta, is really cosine theta plus j sine theta. This is what we were after actually, guys. This is Euler's formula. We will write a little bit more general form of it. You should really know this very well because it really signifies my complex sinusoid can be written as addition of two sinusoids. One in the real axis, one in the imaginary axis. Is this clear until here? I'm hoping or assuming you guys are clear with other. For instance, if I give you this z to equals j, you could write it, maybe let's 2j. You can say, hey, it's here. Imaginary real, right? Let's say this is z1 vector. Or for instance, z2 is -1, which is also equal to e to the j pi, or e to the minus j pi. Of course, due to this periodicity with 2 pi, it could be also z to the j 3 pi, right? This is z2, I mean e to the j 3 pi. What else? I could have here another complex number. Let's say this is z3, which is 3 e to the minus j pi over 2, or 3 e to the j3 pi over 2, or you could continue in this way, of course, plus minus. These are clear, right? And any generic one here is z is r e to the j theta. Okay? Are we clear? This is clear, right? This is Euler's formula. I will rewrite it, but I'm hoping you are clear with this. Now I will say z is real of z plus j imaginary part of z. This is how we defined actually z. So from here, I know real of z is really equal to z plus z conjugate over 2, and imaginary of z is, remember these, z minus z conjugate over 2j, right? I mean, you can, guys, just do this math here. Z conjugate, just look at their x's and minus y here, y, this is x, do the math here, okay? This is my real, this is my imaginary. Is it clear? Alvin, you mean the last graphic, this one, I guess? Just a sec, let me check what you just said. Fine, you may have, okay, no, yes, please ask, please feel free to ask anything, anytime. In the past years, guys, I was joking always in the class saying, hey, this is high school math, you should know this. And then the students always write this. Some of the students somehow don't like it and always put this in the comments at the end of the semester, the surveys. I mean, we just laugh it off, but I'm not saying to really make you inferior or anything. You may forget, but you should be very quickly remembering these, okay? I mean, if the reason I was saying that is in the exams, then people are making so simple mistakes that a high school student should know, that makes us not happy, right? I mean, I'm gonna again make this pep talk, but you are E2 computer engineering student, not any other school, okay? And we are really at the top, right? Top of the chain. So please, you are representing us. Yeah, Berktu, you may be right. Berktu is saying the high school curriculum has changed. My times and your times could be different, but then it's, yeah, maybe I shouldn't say high school, it's the calculus, freshman year calculus. But yeah, Elvin and everybody, just remember, so I just take a z, any complex number, take it, x plus jy. Are we clear? And then I know it has a real component and the imaginary component. You see, the imaginary is multiplied by j. So if I give you now another one, which is z is 0 plus j times 1. This is exactly, okay, it was 2j, exactly here, or j times 2, let's say. Exactly, it's z1 here, right? It should be, its imaginary is 2, imaginary value is 2, its real is 0, real part is 0, imaginary part equals 2. Are we clear? It's then on the y-axis, imaginary axis at the positive side. Now, if I give you this, 0 minus j times 3, it would be really this guy, right? Minus 3. You go 0 to the real, which is none, and minus 3 to the towards the y-axis here, or the imaginary axis. Clear, right? And now the other way around, it is z equals -1 plus j times 0. There is no imaginary part, so I'm on the x-axis. Z equals 1 is, of course, only on the right-hand side. So z equals, let's say, -10. So that would be really, I mean, on the axis, of course, -10 here, right? Is it clear? Of course, anything else is in between somewhere. What we will be doing is we will be mapping the sinusoids onto this complex plane, okay, representing them here, and when their actual frequencies are the same, we will map the amplitude plus the phase part here, add them up, and go back to the real domain. Is it fine, Erwin, now? I hope fine. It's fine. Okay. All right. So I assume it's fine. Where is R? Mehmet, R is the radius, right? Thank you. Very good point. So let me give you this example. Z is equal to, let's say, -1 plus j. Okay, let's find this on my complex plane. Thanks for asking. What is R? R is square root 2, right? So it's gonna be really, and what is theta? It's actually, I can see that -3 pi over 4 already, because it's really equal to arctangent 1 over -1, right? I know, actually, I just know it's in the third quadrant here, right? I mean, you could have come from here too, but let's say I came here. So let's say this is Z5. So Z5 will be really here, right? And Z5 is square root 2 e to the j -3 pi over 4. Is this clear? And it's also equal to this. So these are equivalent representations, polar form and Cartesian form. Euler formula. Yeah. Thank you, Mehmet. Exactly. It's gonna come there. It's really like here. I mean, I just was showing here for R equals 1. That's why. But here, yeah. Mehmet, you're right. I mean, this is, guys, know this well. Know this very well. You will be using it a lot. You're right, Salih. So let's make it minus here. Yeah. It should be up. I don't have space there. I was imagining here. Thank you. It should be, let's say, -1 minus j. Okay, so -1 over. If, like Salih said, if I had a plus j, it should be at the second quadrant. Yeah? Cool? All right, perfect. So here now we will define other two forms of the Euler formula from making use of these equalities. Remember, Euler was, let me again write it just for your notes. R e to the j theta, let's say, is, or let's make it R equals 1, just for this simple writing here, cosine theta plus j sine theta, because I want to now write cosine theta is equal to, this is also very important. Of course, if there is a constant scaling cosine theta, it's gonna come as a scalar here too. E to the j theta plus e to the minus j theta, the conjugate. I'm using this one, guys, on the top right. The conjugate of e to the j theta is e to the minus j theta over 2. Very important formula. And sine theta, I can now use this guy. E to the j theta minus e to the minus j theta over 2j. Pay attention to the minuses here. And j here is different. There is a minus here. Okay? Know these formula also well. I mean, I won't tell you to memorize many other things, but this Euler formula and its two other forms, two variants. So this is really decomposing a complex sinusoid into two real sinusoids on the complex plane, of course, and two variants of the Euler formula, writing a real sinusoid, right? Cosine or sine, it's the same sinusoid. A real sinusoid in terms of two complex sinusoids or exponentials. So don't get confused. We also call them complex exponentials or complex sinusoids equivalently, okay? This is important. So then I think I can show you now this, what we were after is this, guys, right? Complex sinusoids. Now we are really trying to write now our signals with the frequency. This, remember, we made the angle function also time varying. Our x of t is a e to, not e to the yet. Yeah, actually, let's start with the complex sinusoid. Omega t plus phi. Now I will write a. This is equal to, you see, my x of t cosine omega t plus phi plus j a sine omega t plus phi. Okay, this is important. I can maybe say omega 0. So this is really on the complex plane. We have a very nice visualization. I'm going to show you. I mean, somebody did it. People put these things in YouTube. I think it's going to make it clear. So really, you see this signal, we are really mapping it to our complex plane. Real, okay. It's here. X is a complex, x of t is a complex sinusoid. So let's say it is oscillating at a certain omega 0 frequency, okay? So now you can imagine on the real side, it is a cosine. How can I draw this? I can draw it in this way, I guess. The real axis, I will draw a cosine here. Okay, this is the real signal, real sinusoid, and on the other side, I'm mapping it to the real axis. Imaginary axis is a sine with the same frequency, of course, okay? With both, so this is cosine omega 0 t plus there is also a phi, and this is on the imaginary axis. So this is really imaginary axis, this is real, t in seconds. And this is the sine omega 0 t plus phi. It may be difficult to imagine a little bit, but now I'm going to show you a YouTube video for that. By the way, guys, this omega 0, the frequency, angular frequency, you see, in this course, we will be talking about negative frequencies also. This is really like a clockwise, so you can think of this. Okay, this guy, so let's see, a e to the j omega 0 t times, this is really e to the j phi, this is the, what we call the phasor part actually. Let me maybe write it in this way. A e to the j phi times e to the j omega 0 t, this is the phasor part of this signal, and this is, you see, the time varying frequency or oscillating sinusoid part, okay? So for instance, at time 0, x of 0, what is it? Is really this phasor. Let me write it with color, other color. So x of 0 is really the phasor part. And then as t becomes positive, it's gonna start rotating actually with frequency omega 0. If it's negative frequency, these rotations, you can think of oscillations in nature. I mean, it's everywhere, right? If something is rotating, let's say, in this way, a negative frequency will be rotating in the other way you can think of. Okay, there could be symmetric ways, but so you can say this is the, by convention, counterclockwise rotation. This is okay, counterclockwise oscillation. This is clockwise oscillation. Okay. So we said a complex sinusoid has two components. It is a, why is there an A? What did I do, guys? No, that's an omega 0. Yeah, back to you. Right. It's an index. So I think this is omega 0, guys. Important. This is the frequency of this signal, right? Angular frequency of this signal. Good. So complex sinusoid has two components. which are also sinusoidal and real and imaginary components. This is important. So maybe I should say a complex sinusoid has two sinusoidal components, real and imaginary, of course, but in a real and imaginary axis, okay? And they are both sinusoidal also. So guys, let me show you this video. I think it's gonna really look very good to you. Let's see. Let me go to my desktop. It's open. Yeah, actually I opened it. This is really nice. So let's maybe increase my sound. But actual sound is not, it's writing. It's in the captions, explanations. This Eugene Kutoryansky, thanks to him, that actually he has a channel. I believe, I remember there are very nice scientific visualizations. You should really have interest in these things, okay? You should really, as scientists, you should make use of these, watch these animations and things like that, and really get satisfied actually with these, get pleasure at least. So let's see. Oh, let's see. Maybe let's start from the beginning. Huh.
We have an x-axis and a y-axis. Let us also create an axis that represents the angle of theta.
Exactly showing the signal I showed you now, the complex sinusoid. X was this real line in our complex space, Y is the imaginary. And plotting now this A times, or I don't know if it's reduced one, but e to the j omega t plus phi, okay? So theta, you see, but that's actually omega t plus phi is a theta, right? And it starts thing to change it.
Rotates by the angle of theta. For each value of theta, the x-coordinate represents the cosine of theta, and the y-coordinate represents the sine of theta.
Look.
The angle of theta can range anywhere between negative infinity and positive.
So guys, now we are seeing it from one of the axes, let's say real side. That's a sinusoid, and now later they're gonna rotate it and we'll see the sine. Now going to the other dimension.
This two-dimensional pattern
Now to the y.
referred to as a sine
Sine.
wave.
The other one was the cosine. It's beautiful, I think. Changes
We
the
can change the sine wave's
amplitude.
phase,
Phase shifts, you see time shifts corresponds to a time shift.
and frequency.
And frequency, you see it's halved, so it's a smaller, lower frequency.
Suppose we have two sine waves that are identical except for the fact that they have different amplitudes.
Adding two sinusoids,
If
we will
add
do
these two
this.
sine waves together, the result can be represented graphically as shown.
It will be another sine with the same frequency. Okay? It's here, it's just amplitudes are differing. The most easy way to add two
Now,
sinusoids,
suppose
of course.
that the two sine waves also have different phases.
Yeah, but the same frequency, so the result will have the
The
same
sum of these two
frequency.
waveforms can be represented graphically like this.
When different frequencies, actually, of course, things will get different. But this part
So
of the
long as
course,
the two sine waves have the same frequency, their sum will always be another sine wave of the exact same frequency.
Exactly.
With a different amplitude and phase.
yes, that's the. You guys, we can share these with you, but I hope somehow this gives you a nice, actually, mind visualization for the complex sinusoids, right? So it's like two sinusoids in the real and imaginary axes. So it's like another dimension, actually. It showed us this third dimension. It's beautiful. So it's 10:30. Already we've already done 1 hour. I guess you guys are following really well. Okay, let's continue with our complex sinusoids. But is the idea of a complex sinusoid mapping to two real sinusoids? Is it clear? Sorry guys, what is this? Is it clear? I'm hoping that's clear. Two complex sinusoids, and we've just talked about a plus frequency and minus frequency. That may sound odd at first, but you know, it's like some kind of rotation or oscillatory behavior, and things can also do the same thing in the other way around, right? Okay. So I think we should be fine. Let's write, however, maybe one more time. Let me share my tablets, guys. All right. Here. So let's continue. And I think we can say, let me see, where do we continue now? Okay, so maybe let's do this. So for instance, A cosine. Now I ask you this actually. Write this in terms of, a complex exponential or complex sinusoid. How would you do it? I mean, it's just a notation. I can say it's the real part of a e to the j, right? Omega 0 t plus phi. Okay, this is something you should know. And similarly, of course, a sine omega 0 t plus phi is imaginary part of a e to the j omega 0 t plus phi. Okay, we know this now. So for instance, example, evaluate, guys, x of t is equal to real of minus 3j e to the j omega t. Okay, so here you should be careful. There is a minus 3j part. We should convert it to a polar number, a complex exponential type number. So what is minus j? Recall, minus j, just always think of the complex plane, guys. Go there. This is real, and because it's minus j, it should be on the imaginary axis, right? And it should be at the minus side with -1 here. So really, here I can say this angle is minus pi over 2. It's really e to the minus j pi over 2, right? So that's something I can add. Let's just say it's really, don't leave a minus here, that's why. E to the j pi over 2, e to the j omega t, really this is 3 cosine omega t plus pi over 2, right? For instance, this signal. This is my x of t. What else? A minus, right? I'm sorry, guys. I mean, it should be minus here. I just said minus here, and I didn't carry it here. Minus. Okay, that is good. For instance, actually, just recall this example. There were some identities you guys were memorizing maybe for the university entrance exam. Now it's very easy. You don't have to memorize. You just have to know. Just use your Euler formula. Okay, that's it. So I know my cosine a plus b is the real part of e to the j a plus b. Now this is really real part of e to the, use the exponential function manipulation, which is e to the j a times, I mean, I can really expand it in this way. Now, again, use the Euler formula on top of these guys. So let's do this. So it will be really real of, use Euler formula now. For this first one, it's cosine a plus j sine a times cosine b plus j sine b. Okay, continue this. You see where I'm going, right? This is how those identities were derived, is through exactly this complex calculus. So it would be really cosine a cosine b plus j cosine a sine b plus j sine a cosine b plus or minus, not right now. I mean, j square is minus, so sine a sine b, right? So it's really, I need the real part, so I won't rewrite it. I'll just take it out. Real part is then cosine A, cosine B plus or minus, sine A, sine B, right? If I were to take out the imaginary part, it would be these two, right? So, but you see, I'm really neglecting those two, guys. That is it. Is it clear? You see how now this was derived? Okay. So, for instance, you can do, I give you an exercise for the same thing. Sine 2A, for instance. How can you open this up? Now you write, let me write this maybe, imaginary e to the j 2a. Now open this up or expand this as e to the j a times e to the j a. Use your Euler formula. I think you can do this, right? Let's say this is exercise. Please do these exercises. They are fun. It's good for your neurons in your brain, okay? Please use your neurons and synapses a lot for all your courses, classes. This is your university education years. You should not be lazy. You should really work hard. These are the years that you should be really investing for your future, right? And try to understand the basics of things. Okay, so from here, please derive this, guys, and to find, I know, I recall, you guys recall this as this form. Okay, now you see, I mean, this was just to show the usefulness of the Euler formula. My goal actually, okay, you guys can do it here, maybe. I can, okay, we are, let me add some more pages. My goal here is really actually this. Now, we want to start adding, because we said we will be representing any signal soon, later in the course, any signal, but first it will start with periodic, but now we will start slowly, simple. We will start adding sinusoids with the same frequency now, okay? So adding, this is our first goal. Why are we adding sinusoids of now? Remember, because they are our basic building blocks to represent any signal. We make weighted additions of them to represent any signal. Adding sinusoidal signals, let's say, sinusoidal signals, this time with same frequency. Same is important here. This will be using phasors. Now I will repeat what is phasor. I just defined it very quickly. Recall phasor, we said, take a complex sinusoid, let's say A, e to the j phi, the phase part, you see on purpose wrote it separately, and let's say omega 0 t. This part is called the phasor. So now the trick is, it's the same frequency, this is the frequency. So the two signals will really have the same omega 0. They will be both oscillating with the same frequency. So adding phasors will be the trick here, okay? So let's see, let's do, carry out this thing, learn this thing through an example. Here's an example. X1, my first signal. You see, we will be dealing with cosines and sines a lot. We like these signals a lot, like Joseph Fourier really discovered their utility for the scientific development of our species. Actually, this was very important. You see, I'm not exaggerating. All kinds of communications, many kinds of technologies depend on this. So this is for cosine. So I'm writing two sinusoidal signals. What are their frequencies? First, let me ask you. I will want you to add these two, guys. Okay, my question to you will be, find me the signal. Later, maybe next time I'm going to show you a simple Jupyter notebook where I'm adding such two sinusoids. You guys will be doing these exercises, but you should be able to do this because our class is a mathematics-oriented course. Mathematics plus coding, let's say. You should be able to do it with pen and paper, okay? That's why I'm going through these exercises. What are the frequencies of these signals? They have the same frequency, which is great. Exactly 1 hertz. Thank you, guys. Melis, Çağlar, everybody, I think, got it. It's 2 pi. The frequency, same frequency, omega 0, which is 2 pi radians per second, and f is 1 hertz. These are 1 hertz signals. So 2 sinusoids, we've listened to these right in the beginning of the class. Actually, they were 20 hertz to 20 kilohertz. This is a 1 hertz, very, very low frequency signal, but it's fine. Now we go to phasor representation, okay? Go to phasor representation to do this, to do the addition. Addition, okay? So let's find, let's say, x of t really, let's say this is x of t, the result is x of t, the sum signal is x of t, okay? X of t is really real part, so I'm gonna go to the complex sinusoids now. Real part of the first sinusoid in the complex plane, 3 e to the j 2 pi t plus pi over 4, the phase. Okay, plus, let me write them. Okay, let's first write it separately. Real of 4 e to the j 2 pi t minus pi over 3. Okay, this is. So now, of course, I noticed something here, which is that the e to the j 2 pi t part is the here common part, 2 pi t, sorry guys, j 2 pi t, that's the oscillatory time varying part here, but the phasor part I can add. The first phasor is e to the j pi over 4, 3 times e to the j pi over 4, I need to find this, and I'm sorry, plus 4 e to the minus j pi over 3, sorry, it's a little bit at the here side, but maybe I will rewrite it again. Here, let's take these phasors to the plot and then rewrite it here. Okay, so let me try to nicely plot these. Let me see. Okay, let's plot it here. Imaginary, real. Okay. The first signal, the first phasor is Z1, which is 3 e to the j pi over 4. The second phasor, Z2, is 4 e to the minus j pi over 3. Just bring them onto my complex plane, right? You see, then it will be vector addition. That's how actually you see this complex sinusoids is helping us. Otherwise, just think of adding these two. You would not be able to add them. You would have to go to the numerical methods, right? Code them and add them and display the final signal, find the frequency. But now mathematically, I know this complex calculus. I can really do addition of two phasors on the complex plane. Addition of two phasors will do the trick, okay? So let's go. First, pi over 4 and 3. I'll just, of course, roughly draw it, but I know this is pi over 4 at least. So this is my Z1, which is 3 e to the j pi over 4. It's on the first quadrant. Z2 is at this third quadrant with 4 and with pi over 3, guys. I mean, it's not gonna be, of course, exact, but it should be longer, 3, because you see the radius is longer. Z2 is 4 e to the minus j pi over 3. Are we clear? I just mapped the two phasors onto the complex plane, and this will be minus pi over 3. Now, you find the components, right? I have to do, you see, I started with polar form, but addition should be done in the Cartesian form. Cartesian coordinates. Multiplication should be done by the polar coordinates. We will see that. So let's just, actually, I can just open these up. I was gonna say, I need to find these x1, y1, and then also for this guy, let's say x2, y2, right? So we have to really add these two up. So let's just quickly do this before time runs out. Okay, so x of t will be really real of, okay, it's already here, so I'm gonna bring it here, which will be really 3 cosine. I'm just doing the not x of t. Okay, let's just do phasor part. Guys, the phasors only. Phasor part. This is actually, let's say this is really just the phasor part. Two phasors. Phasor sum is this guy. 3 cosine pi over 4 plus j sine pi over 4, right? Plus 4 cosine minus pi over 3 plus again 4 j, of course, 4 sine minus pi over 3. That's it actually. Once I can do this addition and I know what they are, let me write this phasor sum just quickly for you. You guys can do the math later. J 1 over square root 2 plus 4 times 1 over 2. I mean, this is really just numerics, right? Currently what I'm doing. And I calculate this to be really very quickly. I mean, you guys can do this with some calculators. Then you see, this is the Cartesian form. So that is somewhere in my complex plane. Let's put that in our complex plane for, let's see, it will be somewhere probably here, right? When we add these two up, guys, it's gonna be somewhere here. So let's see, it will be maybe a little bit more less oriented on that side, right? Somewhere here. I'm just making it up, of course. Please just z sum, let's say. This is z1 plus z2. So it will be 412.12 and minus 1.34. Is it clear? You see, now we can find its angle, right? We get, this is the phasor sum. Phasor sum, or sum of the two phasors. Now, guys, I can write it as this z sum in a polar form. And I found it to be just e to the 4.3 is the angle. And actually, this is just an approximation. So what I did was r is really from here 412 squared plus 1.34 squared square root. Theta is arctangent minus 1.34 over 4.12. Is it clear? And this was something, some floating number. I just converted to pi over 10. It's fine. But just for you to see the form of this phasor, right now it can go back because I wanted from here the phase, right? Overall phase and the overall magnitude. Now, what is x of t? I think it's clear. Probably, guys, remember my sum signal was really real of the the addition phasor. It's 4.3 e to the minus j pi over 10. This is the sum phasor. And I had, remember this already, the time varying frequency part. And the real part of this is really 4.3 cosine 2 pi t minus pi over 10. Of course, I mean, this is a little bit approximate, but it's fine. So you see, now the sum signal, these two signals were frequency 2 pi, like you guys already said, same frequency, different magnitudes, different phases. Now it's a, sorry, but different phases. Now it is actually, let's go to the next, different magnitudes, so different amplitude, let's say. So resulting signal, different amplitude, guys, and different phase, but the same, of course, phase, but the same frequency. This is important. Okay? So you have questions, I guess? How we found the angle, guys? Yes, I know I made it pi over 10. You can just check, guys, just a sec. Here, it's really actually this. Please take a look. It's coming from this Cartesian coordinate form of the z sum. This is z sum. This is really, guys, an approximation, pi over 10. I just said This is almost pi over 10, okay? I mean, I just pi is, you know, in radians, pi is 3.14 something over 10. So probably this thing came out to be something around 0.314, etc. Okay? You see? That was the idea. Okay? Clear, right? Okay, Berktuk. Currently, we are studying in your textbook chapter 2. Please read. So, reading assignment. Reading assignment, guys. Chapter 2. It could be from any of the textbooks. Let's say signal processing first. Remember, that's or DSP first. It should be similar. It's by the same authors. Okay? You can study it. Exactly. We are following the book. Okay? So in general, guys, let me do this and then try to wrap up. We can continue next time. I will give you also another exercise homework. Our goal will be like this. We can add n of these signals, guys. So AK, different amplitudes. You see, we had different amplitudes. Cosine omega 0t is the same frequency, but phases are differing. This is what we're doing currently. We're adding these to obtain a single sinusoid at the same frequency and with an aggregated phase and aggregated amplitude in a way from the phasor representation. Same frequency is the important thing here. So we're learning to manipulate sinusoid signals. Okay, that's the idea. Later we will be doing things like cosine k times omega 0t. This will be our fundamental frequency, and k times omega 0t multiples of it, integer multiples, will be harmonics of that frequency, harmonic frequencies. This will be later. And your goal will be how to find here A and phi, the overall. Okay? You guys will go from, please also go through this exercise. Or let me write it very quickly. Go to the phasor representation, guys. It's really simple. You see, I have real sum k, ak e to the j phi k times, guys, ak times e to the j omega 0t is the common part. You see, that's what we do. This is addition of the phasors. Different frequencies, yes, we will. That will come to our frequency spectrum representation, okay? So then we will write this guy as A1 e to the j phi 1. So this will be what we are doing currently, right? Plus ak e to the j phi k, okay? N, let's say, I mean n of them. And at the end, you see, we ended up with real of a e to the j phi times e to the j omega 0t. Okay? And that's really a cosine omega 0t plus phi. Okay? Okay. So this is what we've done to sum. Yes, we use the Euler formula also. We can, But here, currently, guys, no, we did phasor addition, Melih, Kaan. What you're saying, can we use the Euler formula? Actually, that's what we're doing, right? We go to the complex plane. Yeah, with Euler formula, we're going to the complex plane, we add things up and come back. That's it. Exactly. So I will give you a exercise. Please do this at home. Please this week go through these, read chapter 2, do this exercise. This is your home, at home, or you are already home, but anyways, x of t is equal to 2 cosine 300 pi t plus 3 pi plus 2 square root 2. These numbers are on purpose chosen so that you can do the additions in the complex plane easily. That's why I'm not changing it now. Let's see. This was 3 pi over 4, 0, 0, 5. It's the phase is different a little bit. I'm asking you to add these, guys. You guys have to add it to find this. So you see, go to the phasor representation. Solution you should find is this. X of t is equal to 2 cosine 300 pi t, right? It should be the same frequency plus 5 pi over 4 because these numbers are easily addable in the complex plane, the one I'm giving you. Please do this exercise at home, okay? I'm assuming you can do it now. Please, if questions, form message boards, ask your assistants in the message boards in Ninova, okay? So next time we go to the frequency spectrum representation, where we will be really summarizing all frequency content of signals. Then we will start multiplying, adding signals. Ne oluyor? Okay, so I think that should be fine. But let me, okay, you guys said it's a little bit difficult. So let me just, for you to guide you to plot the phasors, 2 phasors here. You guys should have. You guys should have these 2 phasors, guys. Let me see. You should have a phasor here with amplitude 2 for one of the signals. And you should have another phasor here, okay, with, let me see, right, that's it, exactly, with another, the second signal's phasor. And what is it? It's 2 square root 2. You should have this, okay? Add these two. I believe you can do it. Please do it. Don't be afraid. If you can't do this, we can solve it next time, but I believe you can. Also, please ask questions to each other, form message boards, okay? I think this should be enough. It's already a lot of material, I realize. Can you guys think of like how to form the phasors, please? I already dropped the 2 phasors. Add them up in the complex plane. It's vector addition and go back to this resultant signal. So resultant vector, okay? All right. So I will stop the share now. Probably stop